Good afternoon, everyone. I, Akshat Gupta, feel privileged to welcome you all for today's technical session on EV crash safety. EV crash safety webinar is a part of Azadi Ka Amrit Mahotsav celebration by Aspire ICAT and organized by PSL Department of ICAT for awareness building on EV crash for industry and students aspiring career building in the field of automotive passive safety. Ministry of Heavy Industry, MHI, Government of India has taken initiative to promote innovation and to develop the related ecosystem. To facilitate this initiative, MHI, through organizations under its aegis, is creating technology platforms for various sectors. In line with this recommendation by MHI, ICAT has launched its e-portal named Aspire Automotive Solutions Portal for Industry, Research and Education. The key objective of this initiative is to enhance the technological capability of Indian automotive sector through exchange of knowledge and expertise in order to make them self-reliant and to facilitate the growth of automobile sector and overall socio-economic progress of the country. This technology platform will facilitate the Indian auto industry, including OEMs, Tier 1 and Tier 2, R&D institutions and academia to come together on issues involving technology advancements. The e-portal will act as a one-stop solution. I'm sure those who are already registered on Aspire will agree with me. Those who have not joined this Aspire portal so far can do so by visiting aspire.icat.in. I now take the privilege to welcome our speaker of the session, Mr. Rajendra Pandaren. Mr. Pandaren has done Bachelor's of Engineering in Mechanical Design from University of Pune. He has 15 years of experience in automotive product design and development from SUV, heavy duty trucks and farm equipment. From past 7+ years, he is working extensively on electrification of these products. He has successfully delivered 2-vehicle platform conversion from ICE to EV, first in automotive industry. He proposed electrification strategy and roadmap for agricultural equipment. During this period, he has worked with various automotive OEMs like Mahindra & Mahindra, Mercedes-Benz R&D, tractors and farm equipments. Presently, he is heading electrification vertical in MG Motors India Private Limited, Halol, Gujarat. We welcome you, sir. I now request to proceed with your presentation. I'm sure this presentation will give us an insight about the EVs and its safety. I request all the participants to write their questions in the question box. We shall take the Q&A round at the end of the presentation. Sir, over to you.
Yeah, good afternoon all, and thank you Akshat and ICAT team for providing this opportunity to me, and thanks for a brief introduction. So good afternoon all. I'd like to start my presentation. Just a minute. Akshat, is my screen visible?
Yes, sir. You can switch to presentation mode.
Yes. So,
yes,
good afternoon all. Welcome again to a good initiative which is started by ICAT, and I feel this will help a lot of students or career aspiration people to enhance their skills and increase their knowledge database. In today's session, I will be taking you through, touching through a few points, a brief on what is the powertrain architecture in the EVs, what is the electric powertrain impact on the overall vehicle safety, then the future challenges about the crash safety regulations. So that's the agenda for today. To start with, I'll start with powertrain architecture. So the classification of powertrains, broad level of classification of the vehicle powertrain technology. It starts with it is classified by energy source or the onboard energy used and the propulsion system used. So onboard energy source and onboard energy source and the propulsion systems from this classification defines the powertrain architecture. So most of the advancements are from last 15 to 20 years due to the push for the clean environment and the stringent emissions norms globally. This has forced the automotive industry focusing on the cleaner and more efficient power technologies like EVs and HEVs. So compared to conventional vehicle powertrain architecture, EV and HEV architecture is more complex due to the involvement of high voltage systems, lithium ion battery, which may lead to a fatal accidents. So high voltage component overview. In most of the EVs, there are 5 significant components that replaces the powertrain of the traditional vehicle. So energy storage system, as everyone is aware that the high voltage battery pack is the single largest component of electric powertrain, which contributes almost 30 to 40% of the vehicle cost, also contributes to the increase of the weight. So this is one of the major contributing factor. Then electric drivetrain. So each company will have their own nomenclature or differences here. So we call it as an electric drive system EDS, which is comprising motor, power electronic box, and gearbox. So next is onboard charger. So everyone is aware about the function. So it basically converts the AC to DC power converter. Then the power distribution system unit to distribute the electrical energy to all high voltage system components using the high voltage wiring harness. So these are the 5 major components which replaces the different components from the traditional ICE vehicle that differentiates the EVs. So the powertrain architecture may vary even among the newest models. So for example, it all depends on the OEM to OEM and their product requirements. So few people have like dual motor drive systems. Some people will have all-wheel drive systems. So these many of the information is already available on internet, or you can study about the various advantages and disadvantages of these powertrain architectures. So the government is pushing a lot for the faster adaptation of the EVs. So an increasing number of EVs are now flooding into our daily life, and this draws much attention from not only the professional who are working in the relevant fields, but also from the ordinary customers. So you can see that all 5 major countries, they have announced various industrial policies, government regulations, and each of them are targeting for a higher EV market share by 2030. So at present, one of the most highlighted concern in the EV is EV safety problem. So is it possible to attain a satisfying EV safety level which is not worse than or is more comparable with the traditional ICE vehicles? So that's what is the biggest challenge and the worry people are facing now in the industry. So the impact of these electric powertrain components on the vehicle safety. So many prospective buyers of EV are scared of by range concern, while others are worried about the safety. With highly flammable batteries, energized electrical circuits, it's obvious to see how these technologies may be deadly. So some of you may be shocked to know that the lithium-ion batteries carry less fire risk or the explosion risk than the gasoline. In circumstances in which the batteries are damaged and caused fire, those flames are confined, and people will get a time or to respond, or people will get a time to get out of the vehicle by seeing the fumes. It won't directly blast, or it won't directly go into the catastrophic failure. Whereas when it comes to the fires produced by gasoline, the flames are quickly spread to the other compartments of the car and could not be extinguished. So before we know that the complete vehicle will be burned down. So what happens to the electric car battery in the accident, and what are all the safety precautions that the electric vehicle designers or engineers are incorporating to save the lives? So let us understand it. So from the regulation perspective, in theory, the passengers in an EV will confirm the same physical injury hazard to the ones in the conventional ICE cars when the crash emerges. So from the physical injury criteria standpoint, all the regulations for the occupant protection and the technologies which reduces the injury after the vehicle crashes are same or equivalent to what they are applicable to the conventional ICs. So the electric shock injury hazard is pretty special in case of the EVs, and they are very seldom focused in an conventional ICE vehicles. But they are very important issues for high voltage powertrains. Hence, for the sake of better understanding of the EV safety, the electric shock hazards required to be discussed emphatically. So, there are regulations which are available for the occupant protection. Japan, Europe, USA, and even in India, we do follow the AS 038. So the technologies which help us to reduce the electric shock injury are like IP levels. Each component, the high voltage system components, they have their own IP ratings. Insulations are maintained. High voltage isolation is continuously monitored. Even in case of accidents, the architecture or from the E architecture, people will try to reduce the energy through a different registers or through different methodologies and try to bring it to very low energy level. So that's all are the attempt from the various designers. So performance criteria to accept the protection against the electrical shock. So there are 4 criteria. The first one is the physical protection. So let us take a first case where there is a chance that a person can contact with the 2 exposed live parts. When I say live, they are high voltage components and which makes a circuit complete. So this is what is required. So through once we assess this criteria demands for a physical protection of all high voltage components. Second criteria is electrical isolation. So, for example, there is a short circuit. One part is exposed, live part is exposed, and second part is indirectly connected to a 12-volt chassis ground. So, how do we avoid that? So, in this case, the protection methodology is to monitor the electrical isolation. So that's why the criteria specifies that minimum resistance depending on whether the DC or AC buses are separated and combined. So there must be an electrical isolation between high voltage and the low voltage system. The next two criteria are about the absence of high voltage and low electrical energy. So this is required in case of let's say indirectly there are two parts which are exposed to the positive and negative of the battery pack and completes the circuit. So in this case we must ensure that after the crash there is an absence of high voltage and the electrical energy is reduced to below 0.2 joules. So electrical shock injuries are pretty special, as I said. So at least one of these four criteria must be met after following the impact test. So how does the electric powertrain impact on the safety concept? So compared to IC and EV, the passenger protection or the body deformation control and optimization of restraint system remains the same. So overall architecture, there is no major impact on the passenger protection system like body deformation control and optimization of restraint system is same for EV and ICE. The major impact due to the adaptation of electric powertrain is on the prevention of the secondary accidents. So in case of ICE, the secondary, so we need a protection of the fuel system, whereas in case of EVs, we need a protection of high voltage system. So in conventional vehicles, during the early evaluation days of ICE powertrain, lot of work was done on the protection of fuel system. Even in EVs and HEVs, in a very short span of time, a lot of work has been already done on the protection of high voltage system. And nowadays they are comparable to the ICE in terms of prevention of the secondary accidents from high voltage systems. Like many OEMs, they have their own protection about the structural protection, electrical safety systems. They are in place in case of the EVs. So how do we achieve the physical protection structure or the design of the physical protection structure? Firstly, if you see the packaging, the high voltage components of EV are placed outside the passenger compartment. You can see that except the PTC heater, which is not shown in this layout, but we do have one PTC heater which will be inside the cabin. But except that, all high voltage components are placed outside of the passenger compartment, and they are all secured inside a framework structure such as side members, body seals. In other words, it protects from the electrical shock in the crash, preventing the direct contact of these high voltage components. Additionally, these components are protected by the structures. So there is very less chance that the occupant will directly come in contact of these high voltage components. Secondly, there are multiple protection systems applied to high voltage component outside the passenger compartment. In particularly for a battery pack, you can see here that we can see a 3-layer of protection. First is the body structure, the body side seals, which protects, acts as a primary protection. Secondary protection is the cross member and the floor cross member itself. Third protection is the battery pack enclosure, which is made out of high tensile strength steel. So these all are used to protect the customer, and in particular the electric shock due to direct contact between occupant and high voltage component is prevented by this concept of component layout and the body structure. So overall packaging of these components will ensure the physical protection against the high voltage system. Next is about the electrical safety system. So modern EVs, they use the isolated ground type electrical architecture. The types of earthing system, just an basic information to all participants, that there are 3 major types of earthing systems which are used by IEC 60364. They are TT, IT and TN. Further, the TM system is subdivided into TNC, TNS and TNC and S. To put it very simpler, T is a direct connection to the earth. I means isolated, N is for neutral, separate and combine. So India uses the TNS type earthing system, but in the EVs we use the isolated grounding system, so which is again an IT type of system. In the grid or network, only Norway uses this type of system, where the high voltage components are completely isolated from the low voltage components. There is an next level of protection also. So the high voltage shutdown system, in addition to the protection against the contact explained in the previous section. So the electric shock prevention after crash performs even better by adopting the shutdown system. So you can see here there is a high voltage shutdown system. This is just an general example or a general layout how the components are electrically connected. So here you can see that an airbag ECU sends a request to the VCU, and VCU will control the electrical system, and it will disconnect the battery relays, which are normally open condition relays. So by sending a signal and cutting off the 12 voltage to these relays, they'll get open up, and the complete high voltage will remain inside the battery pack. So there is no voltage available outside the battery pack. So finally, VCU is the controller which judges the shutdown of the relay in the battery pack. So there are other safety relays and contactors also available in the EV, just to reduce the inherent energy stored in the capacitors. So for example, here you can see there are active resistors or the passive resistors which are available in the inverter for discharging the any energy stored post the crash. Also similarly in DC-DC converter or onboard charger. So all high voltage components will have active and passive resistor to take care of the residual energy dissipation and the DC bus voltage reduction. That's how the safety is addressed in most of the EVs, and we try to protect the occupants from various electrical hazards. So future challenges about the regulation. The current regulations still required to be improved, considering the following aspects. The current regulations are mainly developed for the test, and as long as the EV satisfies the requirement, they will be locally approved for the sale. Therefore, all vehicle manufacturers take on the main responsibility for making their products just qualified. As an ordinary person, it is needed to recognize that the EVs that we can buy or see in the daily life are pretty safe in crash condition, because they must satisfy the relative legislations. Hence, it is urgent to determine the relevant regulations as soon as possible through the introduction or establishment, so that we can adopt the rapid development of the EVs. Although the lithium-ion batteries have become safer in many ways since their invention, there remains a risk of fire and explosion caused by thermal runaway. Hence, it is urgent to determine the relevant regulations. So, most reported incidents of thermal runaway were caused by either internal or external short circuits, resulting from the abuse of the cell or complete by suboptimal cell design. So whatever we see nowadays, there are a lot of cases in other industries about the fires. Mostly they attribute to a poor BMS design or a poor cell quality or suboptimal cell design. These are the main reasons for these fires. So the regulations need to cover more aspect, because many residual risks are still remaining. For instance, the amendments specify the requirement to control the moment of RESS. This is about the structural integrity that is closely related to the short circuit or rupture of the battery pack or fire and explosion hazards from the battery pack. Secondly, the amount of electrolyte that leaks from the EV battery pack might increase if an EV rolls over following a collision. In this case, the regulations about electrolyte spillage deserves a modification. So also there is a need for a coordination of various national regulations, which is of great significance, because each department have their own regulations and guidelines. For example, the GEB boards, they have their own regulations. The Ministry of Heavy Industries, they are notifying their own. So there is a need for coordination of these various national regulations. That's what I believe going forward. So that's all from my side. Maybe we can take a question and answer.
Thank you, sir, for that wonderful presentation. I cannot see any questions from the audience. Maybe your presentation was very clear and precise. I would request everyone, if they have any questions, they can write in the chat box.
Okay, thank you. Thanks, Akshat and the ICAT team for providing this opportunity again.
Sir, we have a lot of questions now. Just a minute, I'll read them one by one if the time permits. And
Okay.
okay, so I'll read aloud the first question from Mr. Senthil Kumar. He says, I have some questions related to the sealing of HV battery, e-service plug, switch, MSD in battery pack. So maybe he wants to know about the sealing of these components, if you can throw some light on it. Rajendra sir, are you there?
Sorry, I was on mute. I just started talking. So yeah,
Okay.
on sealing perspective, or so as we all know that HV battery pack is one of most critical component and which is mounted at the bottom of the vehicle. So most first component which can go inside the water clogged area or to water. So most of the OEMs they all specify or they have rather IP67 protected battery packs. So IP67 itself defines the criteria. For example, the depth for which it can be dipped or the time, maybe only 30 minutes it can sustain. So that's how the sealing is designed in most of the battery packs. For MSD, also one more point here is all the connectors which connects the high voltage battery pack, they are mostly of IP6K, 9K protection. So they provide a higher IP protection. On MSD, there are two types of MSDs. Some people they use a high voltage MSD which divides the battery pack in two halves, or it disconnects the battery pack high voltage outside. And there are few OEMs or there are few architectures where the MSD is just a part of HVIL loop or a 12 volt MSD which is working on the 12 volt strategy. So once you remove the 12 volt MSD, the 12 volt supply to the contactors and other equipments, it dies down and the contactors gets open. That's how the high voltage doesn't come outside. So these are two different types of MSDs, ceilings, MSDs, and what was the third item? Hello, Akshat, can you repeat that third item?
Give me a couple of seconds, sir.
Is it what Mr. Sendil is expecting, or he is expecting something different, or my understanding is something different?
Or maybe I would request Mr. Senthil, if he has further doubts, he can put a mail to us and we'll try to get it answered by our expert. I would move to the second question, sir, now.
Okay.
When retrofitting vehicles with electric powertrains, what is the major concern? This question has been put up by Mr. Vivekanandan MM.
Major concern is about accommodating or packaging these components to suit the existing ICE vehicle. So when we do platform conversion from ICE to EVs, many places we have to compromise on many things. For example, either you have to compromise on the performance or you have to compromise on the range of the vehicle, since the battery pack is not, we will not be able to package the battery pack in the given space. These are a few challenges of the retrofitting. and converting the vehicle. Also from safety perspective, like the vehicle the structure is designed for ICE, and if we see in case of the frontal crash, the crumple zone and the everything changes when we mount the motor and other components in the front compartment. So that is one aspect. And second aspect is about the battery pack mounting. If it is mounted below the floor, underneath the floor, we need to have more strengthening of the floor and the complete structural, what I can say, the complete structure of BIW changes. So these are some of the challenges or compromises we have to do when we convert it from convert a ICE vehicle to EV.
Thank you, sir. Next question is from Mr. Sethuraman Ganesan. He asked, are there any specific risk to the passenger safeties in EVs due to wet conditions during rainy season?
No, definitely no. There are no risks. I would say the EVs are as safe as ICE. If there is a risk, then all designers, or I can say all the engineers in the world, they have failed in creating a product. So my personal belief, there is no any risk. If at all, like we have a lot of safety systems available in EVs, like I explained, for example, isolation monitoring. So if at all there is a possibility that there is a short circuit inside the vehicle goes into the limp home mode, or vehicle alerts the passenger in case of such hazards. And there has to be minimum at least 2 or 3 faults in the vehicle, then only it poses an electrical shock or electrical hazard injury to the occupant. But that is very rare case. So I believe EVs are as safe as ICs in all weathers, whether it is rainy season or any season.
Right, sir. Next question is from Mr. Vivek Patel. He asked, during accident, if battery gets fire, is there any technology to discharge battery in short span of time?
Actually, a good question. There are a lot of research being done on this topic, and in fact, in China and in European countries, like there are regulations related to thermal runaway to protect specifically the occupants. So there are drafts, and some countries they have notified also these regulations that the propagation inside the fire propagation inside the battery pack, it must be in a controlled manner, so that the occupants gets a time to come out. Like as an example, like few precautions which are taken by most of the OEMs is everybody monitors the cell voltage and cell temperatures, everything. So the BMS or the VCU comes to know about the health of the cells and the temperature rising in the cells. They try to shut down the battery pack before it reaches to a thermal runaway state. If at all it fails, it provides an indication, try to provide an alert to the customer in form of indication on the cluster or alert sound to the customer or occupant, so that occupant can park a vehicle in a safe place and get down from that vehicle. Definitely a lot of research is going on reducing or reducing the energy stored in the battery pack. There are efforts on, but it will add a cost. So somewhere the OEMs are thinking on, already the battery pack is very costly item, and putting such system, so active dischargers or passive dischargers inside the battery pack to reduce the energy and the amount of energy. Nowadays people are, like for example ZSEV, we use 50 kilowatt hour of battery pack. So discharging that huge energy within a few seconds, or let's say few minutes, it is a very big challenge actually for OEMs also, and for users also. So that's how, but still there is a lot of work being done in this area.
Thank you, sir. I'll take the next question from Mr. Venkateswaran R. He asked, recently we have seen a lot of EV fire accidents. What could have been the reason behind that? Poor heat management, or is it battery management, or other reason?
Yeah, there could be like 2-3 different probable root causes to it. Mostly it attributes to a poor BMS design, or a poor cell quality, or inadequate validation in Indian environmental conditions. So I could see that these three could be a potential reasons for these fires. So that's what. So even if you see that DRDO has done investigation in these cases, and they have come up with root cause of poor quality of the cells, bad quality of the cells. But there could be another reasons, as I said, a bad BMS design or inadequate validation in India.
I hope that answers his question. Next question is, why MSD is HV battery? MSD in HV battery is not a part of regulation, since MSD is a safe state of for the after sales also. This question has been put by Mr. Senthil Kumar.
Why not in regulation? I am not sure, so I am not the regulatory guy. But it's a safety protective device for a battery pack. So many a times MSD is used in service conditions only. Let's say if I have to service my battery pack or a vehicle, then I use the manual service disconnect. It is not a safety, so it is one of the safety device, but it is manual service disconnect switch. So by removing this, you ensure that your high voltage is disconnected from the vehicle. Also, in case of in event of accidents, so it is used. Let's say if there is a high voltage available in the battery pack, then in that case it is used as a safety device. But generally it is termed as service disconnect only. That's why it could be a probable reason that it's not part of regulation. But anyway, the regulation mandates for 3 different protections, which is like direct contact, isolation failure, and absence of high voltage and the low energy. So if either of these criteria is met, then it is safe for occupant and even for the fire department people who are first responders for these vehicles.
Okay, sir. We'll take the last question for today's session. This question has been put up by Senthan Vasudevan. Will there be any standard size for the batteries? Because it will be difficult to get the same size batteries once the battery life is over, owing to the variation in the battery sizes in different OEMs.
Yeah, definitely this is one of the biggest challenge also. For example, for 12-volt batteries, there is a standard available like DIN and Japanese GIS and other standards are available. In case of lithium-ion batteries, like for example, form and factor, people are trying to standardize that. I'll say same again, DIN and GIS standards. People are trying to work on the sizes, but it is very difficult to make a mismatch or a combination, since the battery pack is made of number of cells in series and parallel. And if you try to use a different size of cells or different chemistry of the cells, it won't match, and you will be end up in damaging the whole battery pack or a complete high voltage system. So it is not recommended to use a different size of cells in one battery pack. When it comes to a complete battery pack level, there are modular battery packs which are available, or like going forward, we can see a lot of things in two-wheeler industry or three-wheeler industry. They have come up with the swappable batteries. Most of them are getting standardized from compatibility perspective or the connection perspective, but still there is a variation inside within the battery pack. So different cells, different chemistries. So I don't see there that people will try to standardize it, and also it is one of the USPs for them to get a higher range.
Thank you, sir, for answering all those questions. And due to time limitations, we couldn't take all the questions. So we would try to answer the unanswered questions through emails. And I would request all participants, if they have any further questions, they are most welcome to put up their questions on mails. Now we have Mr. Ashish Kumar from ICAT to share a few words and give a vote of thanks. Thank you, everyone.
Good afternoon, everyone, and thanks to all the participants. We at ICAT Passive Safety Lab have been trying to provide such platform for the knowledge sharing in the form of webinar, in the form of seminar like IPAS we were doing before the pre-COVID time, and we are looking to provide such platform again and again. And I would like to thank Mr. Rajendra Pandaren for sharing his valuable time from his busy schedule to share the most relevant topic for all of us as an engineer, for all of like users on the road. Lot of curiosity, lot of questions, lot of we can see in the form of questions what we are receiving. There are a lot of anxiety, what will happen in case of safety aspect. That's the like one of the other than the fuel efficiency, the safety aspect is always a anxiety and lot of very different aspect of usage. So those were asked in the form of questions. So I would like to thanks again Pandare, and looking maybe for more future session if needed, because this is the like hot topic and everybody is like exploring and evolving field. And we shall come up like this such technical webinar series. We have done these type of knowledge sharing sessions to the relevant area in the field of safety, and we will come up again with more topics, and looking forward for all the participants to participate it more. So once again, thank you Rajendra Pandaren for sharing his valuable time, and thank you to all the participants. So once again, thank you all for sharing time.
Thank you all. Goodbye.